Welcome everyone. Today, we'll explore PREN. Pitting resistance equivalent number. Understanding corrosion resistance in stainless steels, what it is, why it matters, and how it helps us select the right materials for corrosive environments. Please be informed that this summary is intended to simplify the content based on the presenter's interpretation. What is PREN? PREN stands for Pitting Resistance Equivalent Number. PREN is an empirical formula used to estimate the resistance of stainless steels and nickel-based alloys to pitting corrosion in chloride-containing environments, like seawater or chemical plants. Pitting corrosion is a localized form of corrosion that creates small holes or pits in the metal surface, which can lead to catastrophic failure even if the overall material loss is small. PREN is not a physical property but an empirical index. It predicts how well an alloy resists localized corrosion, especially in chloride-rich environments like seawater. Why is PREN important? Pitting corrosion can cause sudden leaks or failures even when overall metal loss is minimal. PREN helps engineers choose alloys that minimize this risk. PREN used for a predictive tool. It helps engineers select the right alloy for aggressive environments. PREN helps in determine design criteria. Higher PREN means better resistance to pitting and crevice corrosion. PREN can be used for material comparison, used to compare stainless steels, duplex steels, and superaustenitic alloys, and last but not least, PREN helps avoid catastrophic failures from pitting. The PREN formula, the most widely accepted formula is, PREN equal to percentage of chromium plus 3.3 times percentage of molybdenum plus 16 times percentage of nitrogen, and for extended version, use the formula, PREN equal to percentage of chromium plus 3.3 times percentage of molybdenum plus 0.5 times percentage of boots resistance plus 16 times percentage of nitrogen, where Cr for chromium forms a passive oxide layer that protects against corrosion, Mo for molybdenum improves resistance to localized corrosion such as pitting and crevice, N for nitrogen enhances repassivation and stabilizes austenite, and extended versions for super duplex or nickel alloys may include tungsten, stand with W. This formula shows why alloying elements matter. Chromium is the base, molybdenum and tungsten add strength against pitting, and nitrogen helps the passive layer heal. Interpretation of PREN values. PREN less than 25, low resistance, for example 304 stainless steel. PREN in between 25 to 35, moderate resistance, for example 316 and 317 L stainless steel. PREN in between 35 to 50, high resistance, for example duplex, super stainless steels. PREN greater than 50, excellent resistance, for example super duplex, super austenitic, nickel alloys. Notice how duplex and super duplex outperform standard stainless steels, and nickel alloys dominate in extreme conditions. These are common alloys and PREN. Grade 304 has PREN value is 18.8, grade 316 has PREN value is 25.1, grade duplex 2205 has PREN value is 34.9. Grade super duplex 2507 has PREN value is 42.5, grade alloy 625 has PREN value is 51.2, grade alloy C276 has PREN value is 74.6. Factors affecting pitting resistance: chloride concentration. Higher chlorides increase pitting risk. Temperature. Higher temperatures accelerate pitting. Surface condition. Rough or contaminated surfaces pit more easily. Microstructure. Duplex steels often outperform austenitic steels at the same PREN. Speaking about cost versus PREN trade-off analysis, material selection is always a balance between performance and cost. Duplex steels often give the best compromise. This scatter plot compares corrosion resistance PREN with relative cost or versus 304 stainless steel. Observation: higher PREN alloys like alloy C276 offer superior resistance but at significantly higher cost. Sweet spot. Duplex 2205 and super duplex 2507 provide excellent resistance at moderate cost compared to nickel alloys that has premium for extreme environments. Cost factors. This table compares different alloy grades based on their corrosion resistance and cost for various environments. It shows that as the environment becomes more aggressive from potable water to seawater and chemical processes, the pitting resistance equivalent number, PREN increases, indicating better corrosion resistance, but so does the cost. For example, 304 stainless steel with a PREN of 18.8 is suitable for potable water at the lowest cost, while alloy C276, with the highest PREN of 74.57, is used for harsh chemical processes at the highest cost. This highlights the trade-off between performance and expense when selecting materials for specific applications. The cost multiplier is relative to 304 stainless steel as baseline equal to 1. 0. Factors influencing cost. Number 1 is alloying elements. Nickel, expensive, high in austenitic and nickel alloys. Molybdenum, adds cost but improves pitting resistance. Tungsten, very costly, used in high-performance alloys like C276. Nitrogen, minor cost impact but improves strength and PREN. Number 2 of factors influencing cost is manufacturing complexity. Duplex and super duplex require controlled heat treatment and special welding procedures. Nickel alloys need special machining and forming techniques. Number 3 of factors influencing cost is market volatility. Prices of nickel, molybdenum, and tungsten fluctuate significantly, impacting alloy cost. Number 4 of factors influencing cost is availability. Common grades, 304, 316, are widely available and have lower cost rather than exotic alloys, C276, 625, have limited suppliers and have higher cost. Key takeaways, 304 and 316, economical but limited to low chloride environments, duplex and super duplex, best balance of cost and performance for seawater. Nickel alloys, 625, C276 for extreme chloride and chemical environments, but very expensive. Always combine PREN with other corrosion data and real-world testing before finalizing material selection. Limitations of PREN: it's an empirical indicator, not an absolute guarantee, only predicts pitting resistance in chlorides. Does not account for stress corrosion cracking or general corrosion, valid mainly for chloride-induced pitting, not other environments. Frequently asked questions when talking about pitting resistance equivalent number. Question number 1. What is PREN used for? The answer is, PREN is used to estimate the resistance of stainless steels and nickel alloys to pitting corrosion in chloride-containing environments. It helps engineers select suitable materials for seawater, brackish water, and chemical process conditions. Question number 2. Does higher PREN always mean better? The answer is, not always. While higher PREN generally indicates better pitting resistance, it does not guarantee overall corrosion performance. Other factors like stress corrosion cracking, crevice corrosion, and fabrication issues must also be considered. Question number 3. Is PREN valid for all environments? The answer is, no. PREN is specifically designed for chloride-induced pitting. It does not predict performance in acidic, oxidizing, or reducing environments, nor in non-chloride media. Question number 4. How accurate is PREN? The answer is, PREN is an empirical guideline, not an absolute measure. It's useful for ranking alloys but should be combined with lab tests, field experience, and standards for final material selection. Question number 5. Can PREN predict crevice corrosion? The answer is, no. PREN only correlates with pitting resistance, not crevice corrosion. Crevice attack depends on geometry, gasket materials, and stagnant conditions. Question number 6. Why include nitrogen in the formula? The answer is, nitrogen improves repassivation of the passive film and stabilizes the austenitic phase, significantly enhancing localized corrosion resistance. Question number 7. What role does tungsten play? The answer is, tungsten W further improves resistance to localized corrosion, especially in high-performance alloys like alloy C276. It's included in the extended PREN formula as 0.5 times W. Question number 8. Is PREN standardized? The answer is, no official global standard exists, but the formula is widely accepted in industry and referenced in guidelines like NORSOC M001 and offshore material selection practices. Question number 9. How do I calculate PREN for custom alloys? The answer is, use the formula, PREN equal to percentage of chromium plus 3.3 times percentage of molybdenum plus 0.5 times percentage of boots resistance plus 16 times percentage of nitrogen. Insert the alloy's chemical composition, in weight percent, to compute PREN. Question number 10. What's the minimum PREN for seawater service? The answer is, typically, PREN greater or equal to 40 is recommended for continuous seawater exposure. For warm or stagnant seawater, even higher PREN or nickel-based alloys may be required. Key standards and references. Number 1 is, ASTM G48 Standard Test Methods for Pitting and Crevice Corrosion Resistance of Stainless Steels and Related Alloys by Use of Ferric Chloride Solution, specifies laboratory test methods to evaluate pitting and crevice corrosion resistance, often used to validate alloys that meet a certain PREN threshold. Standards and references. Number 2 is, NORSOK M001, Material Selection for Offshore, common in oil and gas industry, requires minimum PREN values for duplex and super duplex stainless steels for seawater service, for example PREN greater than or equal to 40 for super duplex. Standards and references. Number 3 is, ISO 21457, Petroleum, Petrochemical and Natural Gas Industries, Material Selection and Corrosion Control for Oil and Gas Production Systems. References PREN as a guideline for selecting stainless steels in chloride environments. Standards and references. Number 4 is, DNV RP B401, Cathodic Protection Design. While focused on CP, it often cross-references material selection practices that use PREN. Standards and references. Number 5 is, EN 10088 Series, Stainless Steels. Provides chemical composition ranges for stainless steels, which are used to calculate PREN. Standards and references. Number 6 is, NACE MR 0175 or ISO 15156. For sour service, while not directly specifying PREN, it uses similar alloy selection logic and sometimes references PREN in guidance notes. Standards and references. Number 7 is, ASM Handbook, Volume 13b. Discusses PREN and its role in corrosion resistance evaluation. Important note, PREN is not a standardized property, it's an empirical index. Standards like ASTM G48 provide test validation, while NORSOK and ISO guidelines recommend minimum PREN thresholds for specific environments. Thank you.